Okay, in this module, we're going to talk about how to solve for reactions in a simple beam. So a simple beam is a beam that has only two supports, one support at the left and a support at the right. And a simple beam has one support that's a roller, just as you can picture it as a roller skate, and the other one is pinned, so it's not free to move in the X or Y directions. So these are the steps to solve for the reactions of a simple beam. So let's go through and take a look. First thing we're going to do is draw our reactions. And as we said, for a roller, we're going to have only a reaction where the roller is in contact with the surface. In this case, the roller is in contact with the ground, so we only have a reaction in the Y direction. We'll call it RAY. The pin has reactions in both the X and the Y direction. That's the definition of a pin. It doesn't allow movement in the X direction or the Y reaction. So the first step, draw the free body diagram. And you'll recall a free body diagram shows the applied loads, which in this case is in red, the reactions, which in this case are in green, and all dimensions. So you have everything you need to solve the problem. The next step is to sum moments at one of your two supports. So we could sum the moments at support A or support B. I chose support A. So I'm summing the moments at support A. So what I'm going to need is a vector times a distance. So let's go through it one at a time. Here's a vector, RAY. The vector is in the Y direction. So the distance that I want is in the X direction. So I ask myself, what is the X distance between RAY and point A? And in this case, it's 0 because the vector goes right through point A. Go to the next vector, RBY. Again, this is in the Y direction. So I ask myself, I need an X distance. What is the X distance between RBY and point A? And the X distance is 30 feet. So I put 30 feet in here. Next vector, RBX. That's in the X direction. So I need a distance in the Y direction. And I ask myself, what's the Y distance between RBX and point A? And the answer is 0, because again, that vector goes right through point A. And then lastly, 450 pounds is in the Y direction. So I need a distance in the X direction. So what is the X distance between 450 pounds and point A? And the answer is 12 feet. So I have 12 feet. So far all I've done is gone through and draw all my vectors and then make sure that I have all my distances. So the next thing is we have to assume what's positive, clockwise or counterclockwise. And in this problem, we're just going to assume that counterclockwise is positive. So the first thing, we had said that these distances were 0, and since they're 0, they drop out. So they're going to go away. So let's look at the remaining vectors. This vector had not dropped out because it did have a distance. And if you imagine, if you put your finger at point A, because we're summing the moments at point A, and then look at this vector which is pushing up, hopefully you can visualize it's going to cause a rotation in that direction, which is counterclockwise. And in our case, we said counterclockwise was positive, so we're going to go ahead and put a positive in front of that. The other vector, again, if you put your finger on point A and then you have a vector going down, you can visualize that that vector is going to cause a rotation in a clockwise direction. And so clockwise direction, we would put negative. And we know that when we sum moments, they have to equal 0 all the time because it's in static equilibrium. It's not moving. It always is going to equal 0. So what you have then, this is your equation, and we can solve for our only unknown, RBY, and when you rearrange the equation, this is what it looks like. If you do that math, this tells you that RBY is 180 pounds. So we can go ahead and substitute RBY and say there's 180 pounds. Now we know that one reaction. The next step is to sum the forces in the Y direction. So we're going to sum the forces in the Y direction, say up is positive, so we'll go vector by vector. RAY is going up, so it's positive. 450 is going down, so it's negative. RBY is going up, so it's positive. The whole thing has to equal 0 because we're in equilibrium. And we knew that RBY is 180 pounds, so we can plug that in here. And if you do this math, this tells you the equation for RAY, and you solve for RAY, and it tells you that the reaction, RAY, is 270 pounds. And you can see that this makes sense, because see, this 450-pound force is closer to point A than point B, so you would expect that the reaction is going to be higher. It's going to take more to hold the beam up on the left end than the right end, because the load is closer to the left end. So that seems to make sense. And then the last step is going to be sum the forces in the x direction. So we sum the forces in the x direction, and we only have one vector in the x direction, RBX, and it's going left. So we assume that right is positive, and since it's going left, we say minus RBX, and there are no other vectors, so it has to equal 0. Every time we sum forces, we have to end that equation with equals 0, and that tells us that RBX equals 0. So what we have then is we've solved for all our reactions. RBX is 0, RBY is 180 pounds, and RAY is 270 pounds. So these are the steps in this order you would use to solve for the reactions of a simple beam.